Hey everybody, welcome to week 4 of PS 398. You made it. You've been doing such a really good job. This is the second episode that I'm filming since the class has gotten started. The first ones all had to be taped prior. And the questions that you've been asking at meetings or in office hours, it's all been really great. I told this to the students in my other class too. I know that learning this stuff is hard no matter what, and learning it remotely is even harder. But I just want to let you know that I think that everybody's doing a pretty good job. And I know that there's going to be times when you're like, I have no idea what's happening right now. And I think that's an important part of the learning process. I'm also here to tell you that the class should be getting easier in content, not just because you're getting stronger, which is true, but also because we're going to be able to talk a little bit less abstractly about, what is it to model a decision maker, and what is a decision maker, and how do decision makers go through their processes. Those are important questions, but it isn't immediately obvious how applicable they are. You'll see, they're very applicable. But now we're going to be able to start talking a little bit more about real things. And you're like, what is this that's happening? I have some dice. And you're like, what do dice have to do with anything? And it's a reasonable question. So I wanted to talk to you about the start of World War I. So World War I is the war that war scholars have trouble explaining the most. It's the anomalous one. What's anomalous about it? Well, for starters, there was quite a bit of economic integration going on in Europe where the war started. There was lots of trade happening. France and Germany were trading like crazy. Other countries throughout the region were trading like crazy. The alliance structures of the time seemed relatively balanced. And people tend to think that balanced alliance portfolios lead to more stable outcomes. So it's the hard one for us to explain. There are some famous explanations for World War I, most of which involve some discussion about how technology had changed and how military doctrine failed to change along with those changes in technology. There's the so-called cult of the offensive argument. I'm happy to talk about this with you anytime. But I'm not trying to dig into the explanations for World War I. It's just a really important war to learn a lot about. And so I think that a lot of people that study conflict for a living know more random trivia about World War I than other wars, if only because it's the one that they've been trying to explain. I just want to use an important quote from the eve of battle. So the decision-making processes in the run-up to the war were nuanced and shaded. It's not very hard to find good books about some of those pre-war processes. But then comes the final decision. After all the calculations have been made, and all the projections have been registered, and all of the speeches have been given, a leader or a group of people must make a decision about whether or not to start the war. There's only so much planning that one can do. Eventually, you have to decide whether or not to execute the plan. And so on the eve of battle, the German Chancellor, I'm gonna butcher the name, Theobald von Bethmann-Hollweg. Theodor von Bethmann-Hollweg. There's no way I'm saying this properly. Theodor von Bethmann-Hollweg. Anyway, there's a famous quote attributed to him from the night before the war got started officially. And he specifically said, if the iron dice roll, may God help us. Now, that might seem like a aptly dramatic phrase that comes before a big decision like starting a war, and it is one, but it's also telling, right? So the decision was made to start a war, and the German Chancellor, the person responsible for this decision, just mentioned dice. Here's a die. These are dice. He mentioned dice, and the iron dice specifically attributed to the god Ares. But after all of that planning, after all that calculating, after all that predicting, after all of that pre-decision thinking and let's suppose that they were rational, after all of that deep, contemplative, reflexive, complete, transitive decision making, after all of that cogitating, dice got mentioned. Of all of the things that he could have talked about, he mentioned dice. Now, Why is that interesting? Or maybe you don't think it's interesting, but why is it interesting that after all of this weeks of calculations, and he mentions dice? Because he didn't know if he was going to win. He didn't know. You know, when you roll a die, here, I'm going to roll this die. Now, let's say I'm going to get a 6. I'm starting this war, and I'm going to get a 6 because that's just how I roll. I got a 4. You know what? Best 2 out of 3 allied powers. Oh, I got a 1. Why did he mention dice? What's luck got to do with it? Why is he mentioning God's rolling dice? Now, maybe that was just one leader having a bad day. Okay? And maybe it was one German leader having a bad day. German and Prussian military doctrine is some of the best developed, particularly in the 17 and 1800s. Wonderful bureaucratic, technocratic thinkers sort of reshuffled what doctrine was. Some of this was in the wake of getting spanked by Napoleon during the Napoleonic Wars. And so one of the most important artifacts created by that scientification of war that happened a lot in Prussia and later Germany. Maybe the most important artifact to modern scholars to come out of that scientification of the army was Karl von Clausewitz's military treatise entitled On War. We're going to talk about Clausewitz a few times in the class. If you can come by an inexpensive translation, a good, so I recommend the Michael Howard translation of On War. It is beautiful. It's a fun read. And it's sort of Sun Tzu, The Art of War for the 1800s. You know, post-industrialization, post-shifts in organization. And Clausewitz, there are many wonderful quotes that you can attribute to Clausewitz that happen on war. International relations scholars that work in conflict invoke on war. It's sort of like quoting the Old Testament. One of the quotes that came out of On War, actually it's an entire chapter. And in that chapter of On War, Karl von Clausewitz, the great military thinker, perhaps the most important military thinker of his certainly of his generation and maybe a generation or two before or after, likens war to poker. Now, poker is a little bit different from rolling dice. In rolling dice, you know, there's no skill involved. There are certain bets at the craps table or something that might be good bets versus some are bad bets, but it's not like skill has anything to do with it. Navigating probability has nothing to do with being a successful craps player, or it's more at the margins. But for a poker player, it's very important to know both that you don't quite know the outcome for sure, but that nobody else does either, and that you can stand to benefit if you play with skill. Right? So managing expectations strategically is a very important part of poker. And in Clausewitz's analysis, it's an equally important part of war. But right now, so what that means is that we live in a world, in terms of international relations, at least war, and I would argue most processes in international relations, are operating in an uncertain way. You start a war, you don't know you're going to win it. Right? You start a sanction, you don't know that everybody else is going to join in with you. You sign an alliance, you don't know that somebody's actually going to live up to their end of the deal. You don't know one way or the other for sure. You have only probabilistic expectations about what's going to happen. In other words, if we're going to study strategy at the international level with dice or poker, then we need to think more probabilistically than we have up to this point. So I want to talk today about lotteries, uncertainty, probabilistic expectations, and what it means to be rational in an uncertain world. In the previous lectures, we've talked about rationality in a very direct way. If you go to a mini-mart and buy a Coke, you know for sure that you've just bought a Coke. There is no indeterminacy involved. You know what's going to happen. But for the reasons just mentioned, international relations doesn't always have that property. And so what is it to choose something out of a set of things that you don't quite know what's going to happen for sure? And that's the topic of today's lecture. So we're trying to extend our theory of rationality. We're going to extend our notion of preference relations that are reflexive, complete, and transitive. We're going to add some further assumptions on those after we've also said we need to think about a richer set of alternatives. It's not just Coke, Pepsi, and Sprite. It's 20%, 80% versus 75%, 25%. We need to start thinking about how probabilistic expectations ought to be compared. You'll see what I mean here in a moment. So how do we do that? Well, we're going to do that in three parts. So in the A block, I want to formalize what I mean by a lottery. A lottery is the building block of our theory of expected utility. And it's a remarkably simple tool, the lottery is, but you'll see that you can build a relatively rich theoretical apparatus for international relations based on things that are as simple as lotteries. And in fact, on your problem set, you'll have a chance to work through some really important examples of when expected utility has been used to formalize international relations matters. It's finally time for us to start to talk about how to model like international relations scholars. In the B block, I want to talk about expected value. I want to say, hey, how would a statistician evaluate a lottery? If I was somebody who was versed in probability and statistics, how would I look at a certain risky alternative? How would I look at a certain set of probabilities over some set of outcomes? How would I try to make choices in a well-founded, principled way? Now, that's not going to have anything to do with preferences or rationality. This is more like, hey, here's what a statistician would teach you on in terms of how to evaluate a lottery. And then in the C block, I want to talk about preferences over lotteries and link together what we learn in the B block and rationality in general. You'll see what I mean, but we're going to develop a somewhat richer theory of decisions with risky alternatives, these unexpected probabilistic expectations, and we're going to find that if we impose some sensible assumptions on how people compare risky alternatives, we'll actually be able to use a very particular and very easy to use utility function moving forward when we model how countries feel about lotteries. So our goal really is just to take what we have and enhance it. We're going to go from the baseline model up to the deluxe, but a lot of this logic should sound a little bit familiar to you. We're getting to the part of the class where things are going to start to get a little bit more tangible again. And I really hope that you're going to be able to start to see that this is a very useful way to think about how decision makers must operate in this highly uncertain, dice and poker-oriented world that is international anarchy. Let's get started. So here in the A block, I just want to make sure that we have a good sense about what a lottery is and how we can think rigorously about lotteries. That's going to be the input of our decision model at the moment. Instead of thinking about Coke, Pepsi, and Sprite, which is to say, instead of thinking about for sure alternatives, we're going to think about that set of alternatives, just like we had before, but we're also going to say, hey, instead of knowing that you're going to get any given alternative for sure, we're going to allow this to be somewhat random. We're going to allow probability to enter into the equation. So we have the same set of outcomes as before, and in particular throughout most of this block, and the B block, we'll be talking about monetary outcomes, just to keep things very simple. So suppose that we have a finite set of alternatives where those alternatives are all monetary outcomes, right? You get $1, you lose $1, you get $100, you lose $100, whatever the case may be. Imagine that there's some set of monetary outcomes that are possible. We'll just say it's finite, just to keep life super simple. So there's a finite set of alternatives out there. And they're all monetary. We're just going to measure everything in dollars and cents for now, just to keep things very straightforward. Okay? So that's out there. Now, it would be very boring for most people if I model decisions over some finite set of alternatives that was monetary outcomes. If I had a bunch of monetary outcomes and I said to you, hey, choose one of these outcomes, like we did in the previous, like we did with regular rationality, for sure rationality. It wouldn't be very interesting for me to study that decision because you would just take the alternative that gave you the most money or led you to lose the least money, right? So if I offered you $1, $2, $3, $4, and $5, suppose I said to you, hey, here's the set of alternatives. And you're like, boy, you seem like you think you're really smart. and you're trying to hand me some money. Yeah, that's right. So I say to you, hey, do you want $1, $2, $3, $4, or $5? I don't have to bring science. We don't need to bring rationality into this. We don't need to bring reflexiveness or completeness or transitivity. If I offer you those 5 things, you'll take the one that gives you $5, right? Okay. So instead, we're going to think about what happens if you don't know for sure which monetary outcomes you're going to get. Instead, you're only given a vector of probabilities over those outcomes. All I do is tell you the probability that any given monetary outcome will happen, right? So not only do I have a finite set of alternatives, I have a set of lotteries over those alternatives, right? So maybe one lottery, so let's say that X was minus $100, $0, and $100. Let's say that there was 3 possible outcomes, one where you lose, one where you break even, and one where you gain. I could come up with all sorts of different ways to assign probabilities to those 3 outcomes. The thing that are requirements for probability is that I assign each outcome a probability that's greater than or equal to 0. You can't have a probability of -1. You have a 0 probability if something isn't going to happen. And they all have to add to 1, right? So it can't be that you have an 80% chance of losing $100, an 80% chance of 0, and an 80% chance of... That doesn't make sense. When we think about chances, they add up to 100, right? Likewise here, the probabilities are all going to have to add up to 1. So if I have 3 outcomes, minus 100, 0, and 100, then a lottery over those 3 outcomes, right? A lottery over those 3 outcomes is just a set of 3 probabilities. It's a vector. That just means a big list of things in order, right? And every one of those numbers, every one of the elements of that vector is greater than or equal to 0 and less than 1, less than or equal to 1, and they all add to 1, okay? So for example, one lottery over these 3 alternatives is the one where they're all equally likely, right? So maybe it's 1/3 for lose 100, 1/3 for 0, and 1/3 for gain 100. That's a lottery. We can call that L1. That's an example of a lottery over those 3 alternatives. Likewise, I could have put 0 probability on one of the outcomes. Maybe it was you have a 0% chance of losing $100, a 40% chance of getting 0, and a 60% chance of gaining $100. That's a pretty good lottery. Let's play that one. I also could have said that something happened for sure, right? So I could have said you have a 0% chance of losing $100, a 100% chance, with probability 1 you will get $0. That's just take the status quo. And with probability 0 you get $100. Right? So all that we're talking about here is a vector of probabilities. Right? If there's 3 possible outcomes, it's a vector of 3 probabilities. These are all non-negative numbers and they add up to 1. It's really that simple. That's all that a lottery is. And you're saying, that doesn't sound like what I've seen lotteries before, and that isn't what a lottery is. Au contraire, there's a lot more to lotteries than you realize. Let's take a trip to the bookshelf of awesomeness. Trust me. Oh, I just stubbed my toe real bad. That's what happens when you go to the bookshelf of awesomeness, is you stub your toe real bad. I feel good. I didn't just break my toe. No way. So I have some lotteries. I have some things that you will agree with me are lotteries. And you're like, oh, I don't know about that. So, you're with me now, right? This is a lottery. Look. Is a scratch ticket from, I got this at the mini mart, right? So look. It says lottery on it. It couldn't get more lottery. That's a lottery. This is a lottery ticket. Right? And you're like, oh yeah, this is what a lottery looks like to me. Okay. Did you ever actually turn one of these over? So look, in the front, it tells you what you want to know. You could win $2,500 a month for 20 years. Or if you decide to take the short term, I'm actually going to focus on the short term version of that because it'll keep everything's apples to apples. So if you win the grand prize of this, right, you could take this payout, or you could take a lump sum today. You could take $360,000. So this could be worth $360,000. I paid $1 for it. Right? So that's a pretty good deal. That's a really good deal. I mean, this could be worth $360,000 and I paid $1 for it. Oh, you're right. So you're thinking to yourself, well, chances are very good. See, you're starting to think about chances. You're thinking in terms of chances. You're like, chances are very good that this lottery ticket isn't the one worth $360,000. Well, what do you mean by that is what I would say. And that's why we actually have to flip the thing over to learn. Okay? So if you flip one of these over, if you actually go to the back, it will tell you, let's see, which side is it? There you go. Look at that. It tells you probabilities. It gives you, of course, it doesn't put them in probability terms because that's a pain in the, like, they want you to not quite know what's happening. Right? But they'll tell you the odds of each outcome. So let's take this lottery ticket and convert it into a mathematical lottery. All right? Something that's a little bit closer to what I mean. So a lottery is a set of outcomes, and in particular, it's a set of monetary outcomes. All right? So it's a set of monetary outcomes and a set of probabilities over those outcomes. All right? So let's think about this lottery ticket. I'm gonna have to open up the Microsoft Excel of awesomeness because I'm not gonna pretend like I'm not going to the computer for this. I mean, there's no use pretending. Anybody that was doing this would open up Microsoft Excel. It's really weird. I can see my like ring light behind me shining, and so now I sort of look like, oh, that's very trippy. That is super trippy. So if I had Microsoft Excel open, right? Just making a spreadsheet. If I wanted to get a sense about what I thought this thing was worth, this piece of paper, if I wanted to get a sense about what I thought it was worth, the first thing I would do is think about, hey, what is X? What is the set of possible alternatives? What are the possible things that I could win? They tell you one of those things here. They tell you one thing, but they don't tell you everything. So let's just think about it for a second. So you could win your money back. So this was worth $1 and you could break even. So they could give you $1. They could give you $2, $4, $5, $10. You could win $20. You could win $40. You could win $100. You could win $1,000, or you could win the grand prize, which is worth $360,000, just to keep it all apples to apples. So the possible outcomes are 1, 2, 4, 5, 10, 20, 40, 100, 1,000, and 360,000. So there are 10 possible outcomes. We have an X, we have a set of alternatives with 10. Oh wait, no, there's one they didn't tell you about. You also could win $0. Right? I mean, that's sort of implicit in, if you always won your money back, then they wouldn't be offering these for sale. Right? So there are 11 possible outcomes because we have to consider you not winning anything. Okay? So I'm just gonna make a column in a spreadsheet and it's gonna say X at the top. And you're like, this is starting to look familiar. All right, and I'm just gonna put all the outcomes in a column and you're gonna be like, wow, this is so simple. So 0, 1, 2, 4, 5, 10, 20, 40, 100, 1,000, and $360,000. You can just run that right on the screen. Right? I mean, it's you can visualize that. These are the possible amounts of money that you could win with this. And you're like, what does it have to do with IR? I just told you about dice and poker. This has a lot to do with IR. Just give me a second. Now we have to think about the probability of every given outcome, right? We have to say, hey, how likely is it that any given ticket gives you any given outcome? This is only worth one of those outcomes, right? This isn't worth 1 and 4. This isn't worth 1,000 and 360,000. It's worth only one of these. Only one of those outcomes is the actual outcome that will happen. Right now, there are 11 hypothetical possibilities, but there will only be one possibility after I've scratched this ticket. So we have to be thinking probabilistically right now, but once we've scratched it, then all of the fun of probability will have vanished and we'll have to buy another lottery ticket, okay? So what are the probabilities of each of these? Which is related to how many they printed, right? So they probably printed however many there are, and they called one the jackpot one. So my guess is they printed the odds of you winning the jackpot are 1 in 3.84 million. So they probably printed 3.84 million of these tickets, and one of them is the winner. Right? So the probability here is very much, they design the probabilities. They decide the probabilities. The designer of the game. Okay? So let's think, but they have to tell you, they then tell you the likelihood of each of the possible outcomes. So let me just work through these. So the probability of winning $1 is 1 in 11.11, which is like a 9% chance. You have like a 9% chance of winning your money back with this. You have a 9% chance of winning your money back. All right? How about of doubling your money? So you have 1 in 12.9 chances of doubling your money for going from $1 to $2. So 1 in 12.9, that's like a 7.75% chance of winning. You have 1 in 80% chance of winning $4. 1 in 80 of $4. So you have a 1.25% chance of winning $4 with this. How about a $5? You have a 1 in 200 chance of winning $5. 1 in 200 odds, that's 0.5%. What about $10? Well, you have a 1 in 80% chance of winning $10. So that's the same, that's another 1.25% chance of winning $10. For $20, it's up to 1 in 400. 1 in 400 chance. That's a 0.25% chance. 0.0025 probability. $40, 1 in 800. So that's a 0.0125% chance. The odds of you winning, the odds of you winning $100 with this is 1 in 24,000. So your probability is 0.00004 of winning $100 with this. You have a 0.004% chance. $1,000, you have a 1 in 480,000%. You have a 1 in 480,000 chance of winning $1,000 with this. That's a probability of 0.00002. It's pretty low probability. Suddenly, this is looking like it's only worth $1. I thought this was going to change my life. And finally, your probability. Your odds of winning the jackpot, $360,000 in present money, is 1 in 3.84 million. The probability of that happening is 0.0000026. Okay? So we have a vector of probabilities. We had 11 possible outcomes. Oh, I need my 11th probability, which is just 1 minus the sum of those. Because we know that they have to add to 1. So if you tell me all the other probabilities, I can find the last one. So, and it tells you also that you have a roughly 1 in 4.97% chance of winning anything, and that checks out. So your probability of winning nothing is 0.799. Right? You have a 20% chance of winning something. Okay? 80% of the people that buy this ticket end up losing money. That makes sense. Otherwise, they wouldn't sell this ticket. So 80% of people that buy this ticket are losers.
Loser.
In the context of this lottery, I'm sure they're wonderful, winning, charming people.
Winner.
So this is worth $1, right? But the probability that it actually is worth $1 in terms of its realized value after we've scratched it is only 9%. Right? Chances are very good that this isn't worth the $1 that I paid for it. What is it worth in expectation? Oh, we'll worry about that in the B block, right? But as of right now, I'm thinking in terms of these probabilities. I've got to evaluate these probabilities and figure out if I want to buy this for $1. This could be worth $2, $4, $5, $10, $20, $40, $100, $1,000, or $360,000. It could also be worth $0. I've got to evaluate this. You know, maybe I have an 80% chance of losing a war, right? I've got a 9% chance of a stalemate. I've got a 7.75% chance of increasing my territory a little bit, and so on. I have a 1 in 3.84 million chance of beating my opponent country so badly that they become part of my country, and now I'm totally awesome.
Awesome!
Right? That's what it's set up. This is what the German chancellor said. That's what he said. Let's scratch it. Let's see what it's worth. So as of right now, this is a vector of probabilities. Right? There's 11 probabilities. Now the point of this game is I'm going to scratch this winning number first. And the idea is I'm going to have 5 chances to match that number. So the winning number is 10. Okay? I don't know if you can see that. So now I've got 5 chances. I've got 5 chances to get it. Okay? I didn't. I lost.
Loser.
I'm a loser.
Loser.
I really wish I could get Radiohead licenses for my videos, but that's a little bit beyond my budget.
Loser.
So this is worth $0, right? I'll show you, just in case you were worried that I was gonna like hoard. I didn't get any of them. So this is a lottery still. This is still a lottery in the sense that it's a vector of probabilities. This is a vector of probabilities over outcomes. It's just that the probability that this is worth 0 is 1. The probability that this is worth $1 went from 9% to 0%. The probability that this was worth $2 went from 7.75% to 0%. But this is still a lottery. This is a lottery that is worth $0 for sure. I'll show you another lottery that's similar. I'll show you a lottery that has a probability 1 on a certain value, right? It's the dollar that I paid for it. This is a lottery too. This is a lottery that is worth $1 with probability 1. This is a lottery. These are just boring lotteries now. The mathematical term for a lottery that's boring in the sense that it assigns a probability 1, those are called degenerate lotteries because they're just not sort of all of the probabilistic interest has gone away. Now it's a lottery, but only in a degenerate sense. But these are lotteries. So all that a lottery is a vector of probabilities over outcomes. You give me some monetary outcomes, 0, 1, 2, 4, 5, 10, 20, 40, 100, 1,000, or 360,000, and you give me a set of probabilities over each of those, and you've given me a lottery. That's a lottery. They might have different names, like here's a lottery, there's a different lottery. So I can compare lotteries, right? So this is where we're gonna be headed, is if I show you one lottery, this is the 7-11-21 game, or I show you another lottery, this is the Cupcake Cash game. So here's 2 different lotteries. What do I mean by that? Well, I mean, one of them has one name and one of them has another name, and so they are different lotteries, at least in terms of their names, but they're also different lotteries in terms of the fact that there are different outcomes that are possible for each of them, and they assign different probabilities, right? So for example, with this 7-11-21 game, the jackpot, the highest prize you could get with this is $3,000. You could win $3,000 with this. The probability that you win $3,000, the odds of that are 1 in 240,000, so it's still a very low probability event. So this has possible outcomes of 0, 1, 2, 4, 5, 10, 15, 25, 30, 40, 50, 100, 200, and 3,000. So there's some outcomes, and they have probabilities over those outcomes, right? There are different outcomes possible with the Cupcake Cash, and also different probabilities. So for example, you could win $5 with Cupcake Cash, just the same that you could win it with 7-11-21, but they have different probabilities associated with that. So the approximate odds of winning $5 with Cupcake Cash is 1 in 31.58, and the approximate odds of winning $5 with 7-11-21 is 1 in 88.89. So this is far more likely to give you $5 than this. They're both low probabilities, but one of them is more likely to give you $5. But there isn't a $3,000 option on Cupcake Cash, right? So what I mean to say is they don't have to have the same X's, right? The 2 lotteries can have a different X, and then if you could just take the union of all of them if you wanted to compare them, right? You could take a big union of all the X's of the lotteries. That's no big deal. So we got different lotteries. I'm still going to call this a lottery because it's a degenerate lottery, but I'm not going to worry too much more about it because I've scratched it and it's boring. But I have 4 other lottery tickets that I haven't scratched. I've got 7-11-21, I've got Cupcake Cash, I've got the crossword bonus game, the $50,000 crossword bonus game, and I've got The End of Alzheimer's Begins With Me. I was looking to see if there was another title that I had missed, but there isn't. The name of this game is The End of Alzheimer's Begins With Me. Now, I hope that's true. I hope that The End of Alzheimer's Begins With Me. I hope that's true. I don't think that's what I would name my lottery. Far be it from me. So these lotteries, now I've got 4 different lotteries. 2 weeks ago, I went into a mini mart, and there was a Coke, a Pepsi, a Sprite, and a Diet A&W. There were 4 cans, and if I bought a can, I knew what I was getting. Now I've got 4 lotteries. I've got 4 lotteries. How do I choose among lotteries? How do I evaluate lotteries? Right? So, I mean, I'm not trying to make this too opaque, but this is a very important question. Because if war is a lottery, if trade is a lottery, if sanctions are a lottery, if alliances are a lottery, if armistice is a lottery, if these things are all lotteries in the sense that you know what the possible outcomes are, but you don't know for sure which is going to happen, if they're lotteries, if they're sets of probabilities over potential outcomes, if those things are all lotteries, then we need to think about how people pick lotteries. So this is really important. How do you evaluate a lottery? Now I want to keep focus on money just to make sure that you see an intuition that you have that's good intuition, but I want you to know that this is IR. The End of Alzheimer's Begins with IR. Oh, have any of you not scratched one of these once in your life? We're gonna make IR like this. So that's what a lottery is. It's a vector of probabilities, and given some set of outcomes, I might have a set of lotteries to choose from. So where I used to have a set of alternatives, now I have a set of lotteries. And the same way that a country, when they choose war or peace, they're choosing between 2 lotteries. Just the same way that when I choose between Cupcake Cash and 7-Eleven-21, I'm choosing between 2 lotteries. If I can only have one of these lotteries, I need to evaluate the lotteries. I need preferences over lotteries. How the heck am I supposed to evaluate these lotteries? What tools are out there in the world to help me to evaluate these lotteries? Because I'm getting very lost very fast, and I don't know what to do about how to evaluate these lotteries. Let's go to the B block. So suppose that you were a statistician. And you're like, I was a political science major for a reason. Me too, so was I, and yet here I am, saying to you, suppose that you were a statistician. So suppose that you were a statistician. And I hand you these 4 lotteries. I hand you these tickets that haven't been scratched yet. I hand these to you, and I say, hey, which of these should I get? Which of these should I choose? And you're just a statistician. You're not an economist. You're not a political scientist. You're not an IR scholar. You're a statistician. And so, you know, chances are excellent that if you're a statistician, you wouldn't tell people to choose the prettiest one. Right? I mean, you might. Cupcake Cash, that's pretty. 7-Eleven-21, that's pretty ugly. This purple is kind of nice. But that's not why people get paid a lot to learn expected utility theory, right? There's a reason that the people that run baseball teams are the people that run baseball teams, and it's not because they choose pretty lottery tickets. It's because they turn to the back and see what's going on, right? Same with leaders. So how do we evaluate one of these lotteries? How do we evaluate these lotteries? Well, if you've taken a statistics class before, which is an if, but if you have, then you've probably done the exact calculation that provides the most standard tool for evaluating these things. And so you would calculate the expected value. You would try to figure out what this is worth in expectation in dollars, right? We want to take those probabilities and those dollar amounts from our initial Excel spreadsheet when we were evaluating this game. How are we going to take that and convert it into one number, one easy to remember number? That sounds like a utility function. I'm going to take an alternative and I'm going to assign it a number. I'm going to take a lottery ticket. This is a piece of cardboard. with some scratchy parts. I'm going to take that, I'm going to convert it to a number. I want a number that summarizes what I need to know about this lottery ticket. I need a number. I need a number for this one. I need a number for this one. I need a number for this one. And I need a number for this one. I need numbers for these lottery tickets. Because there's other things out there that are easier to evaluate. This is a lottery, as we were discussing last block. Here's a lottery. But is it worth? It's not worth anything other than $1. This is easily remembered as something that is worth $1. This is worth $1. This is worth $1. And you're like, you think this is profound? Yes, this is profound. This is worth $1. Then the hard question is, what is $1 worth? But let's stay out of that one, because that'll drive you bonkers. But I need a number. I need a number. I just need something to tell me how many happiness points I get from not even scratching this lottery ticket, but just having it. Now you say, that sounds stupid. What do you think a stock buyer is doing? They're thinking about the probabilities that a given company is going to do better, do worse, or stay about the same. They got to see the price. Look, these are all worth different prices. This lottery was worth $3. It cost $3. Sorry that I just bumped the. This lottery cost $3. This lottery cost $3. Cupcake Cash cost $2, right? And 7-Eleven-21 was worth $1. So I need something to compare against that dollar, right? I need to know. I need a number to tell me how I feel about this versus this. And it'll be nice if that was measured in the same units. So how would I calculate the expected value of this, which would be a number that tells me how much I like it, right? Okay, well, I have everything I need, right? So I'm gonna run the probabilities for 7-Eleven-21 on the screen. I have everything I need. This is a lottery. There's an X, and there's some probabilities. We're almost there. This is gonna be a very short block. Okay, so I have those probabilities worked out. They're all on your screen, and so now we're pretty close. All we need to do, the formula for the expected value of something is, it's like the sample mean. It's related to how you calculate an average. We want to know what the average value of this is. What is the average of all of the possible outcomes? Right? What is the average, the probabilistically weighted average of all these outcomes? So instead of each outcome being like a 1 over, how many outcomes are there? So there's 14 different outcomes in the 7-Eleven-21 lottery, okay? So I'm not gonna divide by 1 over 14 like I would if I was doing a regular average. I wanna weight this by how likely every outcome is. So I'm just gonna multiply every possible outcome in dollars by the probability, right? And that's still gonna be measured in dollars. So for example, for $1, the probability that you win $1 in this lottery is like 9.5%. So I'll take 0.095 and multiply it by 1. So 7% of the time I win $2. So I want 0.07 times 2. That means that captures that percent of the time. I'm thinking this through a little bit. So I can calculate that for every row in my little data set of this lottery, right? So for each of the possible outcomes, just multiply that column's dollar amount, just multiply that row's dollar amount by the probability of getting that dollar amount. So we calculate that real fast. It's just straightforward. Boom, 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 boom. And we wind up with just this new column where it's just the monetary outcomes times the probability of that. And then if you just add those up, then that tells you the expected value of this. It would tell you, if you bought many of these tickets, what would minimize the error? What would be your best guess for how many? If I said to you, I'm gonna scratch this lottery ticket, okay? And I'm gonna reward you on how close your guess is to how much I win. If I scratched every one of those tickets and I said, hey, minimize how much your mistake is, pick the right guess, that would be the same as this sum. That's a neat statistical result. So this sum is actually a very important number. This is called the expected value. And it turns out that the expected value of this lottery ticket, the best guess, the single best guess for how much money this is worth in terms of probability, dollars and cents, it's worth 64 cents. It's worth 64 cents. This lottery is worth 64 cents in expectation. Its expected value is 64 cents. Somebody paid $1 for it. Does that mean that they're irrational? So this is worth $1, This is worth 64 cents. Does that mean you should never buy a lottery ticket? No. Absolutely not. Right? It means that if you're risk neutral, if you don't value taking risk, right? Nor are you scared of taking risk. If you were just a robot making decisions, yeah, a robot would tell you not to buy this because its expected value of 64 cents is a lot less than $1. You're paying a 36-cent premium. You're paying a premium for the fun of scratching the lottery ticket and potentially something happening. So if you would be willing to buy this for $1, you're what we would call risk acceptant. Right? If you would be willing to buy a lottery ticket for $1 when you knew it was worth 64 cents, then you would be what is called risk acceptant. Okay? If you would be indifferent between this lottery and 64 cents cash, right? If you would be indifferent between this lottery and 64 cents in cash, then you would be what we call risk neutral. Presumably, if you bought this lottery ticket for $1, that means that you like it more than 64 cents cash. So basically, risk acceptant means you would rather play a lottery than have the amount of money that is the expected value of the lottery for sure. You're risk neutral if you're indifferent between the lottery that is worth 64 cents and 64 cents. And you're risk averse if you wouldn't buy this for 64 cents. If you would rather have 64 cents for sure than a lottery worth 64 cents, then you're risk averse. All right? But there isn't, how much risk you're willing to take on is not a rationality question. All right? It doesn't really play a huge role in the theory of preferences over lotteries. It plays a big role in international relations. Right? So we typically don't assume that countries are risk acceptant. So I would rather have a negotiated settlement for sure than start a war that I might win and get everything, right? We'll be talking about that calculation pretty often. So the expected value is a very useful tool for us determining whether you're risk acceptant, risk neutral, or risk averse. Okay? So we have a set of lotteries, and every one of these lotteries has an expected value. Why? Because they all have probabilities and they all have outcomes. So you could go to the back of any given lottery ticket and come up with the probabilities and use the numbers and make this little 3-column spreadsheet and calculate the expected value. That's what statisticians do all the time. Anytime you give them a random variable, that's what it's called. A random variable is just something drawn out of a distribution. Here's a probability distribution with a bunch of possible outcomes. So if you give them a random variable, right, a bunch of people's heights, a bunch of people's weights, a bunch of people's wealth levels, a bunch of countries' wealth levels. You can give a statistician a random variable, or a sample, a random sample, a bunch of draws from a given random variable, and say, hey, calculate the mean. Calculate the expected value, the probabilistically weighted mean. And that's what they would do. So all this is taking a column in a spreadsheet, which is to say a variable, right? And converting it to one number that tells you a lot about it. This expected value calculation then is used in part to help us to determine whether somebody is risk acceptant, risk neutral, or risk averse. And in international relations scholarship, we typically assume that countries or the leaders of countries are either risk neutral or risk averse, which is to say we think that they prefer sure things over many of the lotteries that are available to them. They'd rather have the sure thing of the status quo rather than start a war that might go great for them if the penny flips on their side, if the iron dice are in their favor, but might not, right? But the fact that we know that leaders are evaluating these things probabilistically means that we need to think about international process the same way that a statistician would think about a lottery ticket. And that's going to be a lot of the rest of the class. That's how we're going to think that countries are behaving. That's how we're going to think that leaders are behaving. That's how we think that groups are behaving, is they're going to be maximizing their expected utility. Yeah? They're going to be looking at probabilistic outcomes and evaluating them. And we know that's what they do. They don't know when they start a war whether they're going to win it, but we see wars get started. They take on some risk. That's what choice under uncertainty is all about. Now, I want to talk about something important while we're here. So the X column right now in my lottery, right now that's measured in dollars, right? Now, not all things are going to be measured in dollars that we care about. So whether you win a war or not, that's something you could put a dollar value to if you wanted to, but it'd be really hard. We're not going to be thinking about monetary outcomes all the time. We're going to be thinking about peace, war, you won the war, you lost the war, the sanction worked, or whatever the case may be. We're going to be thinking about outcomes. And so that X column might not always be measured in dollars. I could just as easily say that for any given monetary outcome, you get a utility number from that. So maybe I've got some utility function u that goes from x to the real, so it reads in one of these monetary outcomes, and instead of just spitting out the monetary outcome, it spits out a happiness number. Why do I say that? Well, the gains from money are diminishing, right? So the gap from $0 to $1 is huge. Think about all the things that you could buy for $1 that you couldn't buy for $0. It's very hard to buy things with $0. Right? So if you went from 0 to 1 in a mini mart, the number of new possibilities to you is very high. Likewise for 1 to 2, 2 to 3, 3 to 4. But eventually, once you have $1 million, the gains that you get, that gap between $1 million and $1 million plus 1, that goes down. You don't get a 1-to-1. You don't get a cent for cent happiness boost for that. There's diminishing returns on money. If only because there's only so many things, so many new things you could buy at any given price point. Okay? So because of that, suppose that instead of giving you, so let's say that $3,000 in this lottery is worth U of 3,000. And maybe that's something less than 3,000. Maybe you don't get the same amount of happiness points. Whatever. I'm just saying that I could put utility numbers in that column instead of dollars. Right? And then that's measured in utils or something. It's in some abstract currency, so it's no longer in dollars. We've converted it to some abstract currency called utils. All right? But if I perform the same calculation, if I take whatever those utils are, which might be 1 for 1 for the record, but might be something else, and I multiply it by the probability and I add them up, I get something that is no longer expected value measured in dollars. I get expected utility. Right? So the idea here is that any given outcome in our set of outcomes x, which won't be dollar amounts forever, let's assign each of those a utility number. Let's say that if you win the war, you get 1 happiness point. And if you lose the war, you get 0 happiness points. Right? And then you evaluate probabilities over those two outcomes. You multiply those probabilities times the utilities for each given outcome. You add them up. That's expected utility. So the statistician's assessment of a lottery ticket mathematically is exactly the same as how a game theoretic actor behaves under uncertainty. These are the same exact thing. So the question becomes, well, how do we think that actors are going to make choices over lotteries? How do we think that if we have a set of lotteries, be it 4, 5, 1 million, infinite, there's a lot of lotteries that you could choose from. How do we think that a decision maker is actually going to choose one? Right? So what are preferences over lotteries? Let's go to the C block. I should scratch the rest of these tickets. Any money that I make, I'll give back to the school. In the name of PS 398. I won $5.
Yay!
So I needed to match a 13, and I got a 13, and that's worth $5. I'm not going to give $5 back to the university. They would spend more than $5 in processing it. I don't really know what I'm doing here. This game is very complicated. Oh man, now I have to figure out if I can make any of these words with these letters that I got. Oh. This is stupid. This game is really stupid. I mean, it's not even fun. You have to be risk accepted to want to play this, because you're not doing this because it's entertaining. Like blackjack, I like to go to the casino and play blackjack sometimes. Very rarely. But at least that's fun, you know? This isn't fun. This is stupid. This is just, I don't like Scrabble to begin with. I don't even want to win that game. I don't care if I'm giving up $50,000 or not. That's a stupid game. I'm done with that game. But thankfully, the end of Alzheimer's is about to end with me. Wait, no, the end of Alzheimer's is about to begin with me. Oh, I won $3.
Yay!
So, I think I had bought 10 total tickets for the 2 classes. And so that meant I spent so that's 6, 7, 8, 10. I spent $20 on these lottery tickets. All right? And I've won $8 back. So that wasn't a very good investment in terms of my expected value probably would have been something. Well, let's think about it. If I'm getting 65 cents on the dollar, what's 0.65 times 20? 13, right? So if I was getting 65 cents on the dollar like I was in 7-11-21, let's suppose that was the same for all the lottery tickets. I'm not going to work out all the expected values. Then in expectation, I should have gotten $13 across these 10 lottery tickets. But it didn't happen. I only got 8, right? And so that's what I mean. This is all very distributional. Every given lottery ticket is a distribution, but then a collection of lottery tickets is a distribution too. All right. So up to this point, we've defined what a simple lottery is. A simple lottery is just a vector of probabilities over a well-specified set of outcomes. The most natural way to proceed was just to talk about monetary outcomes to begin with, and so we calculated some expected monetary values of lottery tickets. And then at the end of the B block, we were talking about how we could generalize that to make it expected utility instead of expected value. So instead of making it just in terms of dollars and cents for everything, we can just take every outcome in our set of alternatives, which might not be monetary. So we can take those, assign each of them a little utility number, and then multiply that utility number by the probability of that outcome happening, adding them up and getting something called the expected utility, right? And so the idea behind expected utility is it reads in a lottery and it spits out a number, right? So it's just a function. It's just a function that reads in a lottery ticket or a war or an alliance, and it spits out a number. But right now, we don't know if that number is anything useful to us in a rationality sense. We know that a statistician would recommend that we make decisions to maximize expected utility, right? They would advise us to be risk neutral and maximize that expected value. But we don't know how that relates to utility numbers like we've seen up to this point, right? So the idea with a utility function is it reads in alternatives and it spits out numbers, and higher numbers tell you which alternatives you like more. So if there's an alternative that gives me the highest utility number, then presumably that is my favorite alternative, and I should choose that alternative. And it's interesting to wonder, hey, does this expected utility number that we can calculate for a lottery ticket or a war or whatever, can that be a utility function? Can that tell me how much I like a lottery? Can it be true that the expected utility of one lottery is higher than another lottery, if and only if I like that lottery more, right? So is it always the case that expected utilities give higher utilities to lotteries that I prefer? Under what conditions is that true, right? And it would be great if the expected utility function was it's so convenient to use. It would be great if that could just be our utility function moving forward. So the question of this block is, under what conditions is that simple Microsoft Excel spreadsheet expected utility function, the one that we're going to be using for the rest of the class, the one that you'll be doing in your problem set? My question is, when is that a reasonable utility function? When do we know that it carries the ordinal information of my preferences over the lotteries? All right? So we're talking about preferences over something again. We're talking about a doodle. We're talking about a bunch of alternatives where the alternatives are potentially risky, You could put for sure things in there with a degenerate lottery. So you could put $1 for sure in the set of alternatives. All right? So when can we do that? Under what conditions? So I'm going to make the first three assumptions that we made from before. So suppose that I have a set of lotteries over some finite set of outcomes. And let's suppose that we have preferences over those lotteries. I like End of Alzheimer's more than Cupcake Cash. I like 7-Eleven-21 at least as much as I like the 20 for life thing, right? I need statements of the form, one lottery is at least as good as another lottery, right? I need to know that $1 is at least as good as a lottery. I need to know that war is at least as good as peace. I need to know I need preferences. I need binary comparisons. I need one lottery, another lottery in a binary comparison sense, right? Because I'm going to be choosing war versus peace, and they're both lotteries. So how do I say that I like war less than peace? Okay, I'm going to come up with a preference relation just like before, and I'm going to assume that it's reflexive, so that any lottery is at least as good as itself. I'm going to assume that the preferences over lotteries are complete, so that for any pair of lotteries, I'm at least indifferent between them. I never get to say I don't know about two lotteries. And I'm going to assume that my preferences are transitive. So up to this, I'm assuming that I'm rational over the set of lotteries. Now, that doesn't yet guarantee I can use a utility function. It's close. If the set of lotteries is finite, then it is enough, but I want there to be lots of lotteries, because I want to be able to say all possible lotteries over two alternatives, that's just a probability and a 1 minus the probability. I want to be able to evaluate a big set of lotteries. So, I need more assumptions. My 3 assumptions aren't enough. I need more assumptions. I need 2 more assumptions. So I'm going to tell you about those 2 more assumptions. All right? I'll show some pictures. I'm going to talk about them in broad brushstrokes, but I'm not going to go too much further than that. It won't be necessary for your problem set. I'm just saying this for completeness sake. And you're like, I thought we already assumed completeness. Oh, nice math joke. Proud of you. But I think you'll see from the problem set that you have everything you need now to do the problem set. Right? I just want to tell you a little bit more. It's better than Arrow's theorem. I mean, nothing is better than Arrow's theorem, but you won't suffer as much as Arrow's theorem. So the 4th assumption I want to make is called continuity. So the idea of continuity is the following. So I've got 2 of my scratched lottery tickets. So suppose that I like this lottery ticket more than $1, which makes sense because it's a winner. This is worth $3 for sure. So suppose that I like this lottery at least as much as this lottery. And suppose that I like this lottery at least as much as I like this lottery, which is a scratch ticket that's valueless. So with probability 1, this is worth $3. With probability 1, this is worth $1. And with probability 1, this is worth $0. So the idea of continuity is the following. I need to be able to come up with a mix of these 2 lotteries, the best one and the worst one, that's indifferent by my preferences to this $, to this middle option, this $, for sure. Can I come up with a randomization procedure? Can I come up with a, if heads, play The End of Alzheimer's Begins With Me, and if tails, play 20 Years of Cash? Can I come up with a coin that has just the right probability? Can I come up with just the right mix of these 2 things? A 62% chance of this and a 20%, whatever it is. Well, they have to add the 1. A 60% chance of this and a 40% chance of this. Is there some mix that would make me indifferent between these 2, a mix of these 2 lotteries and this? I'm talking about something called a compound lottery here. I'm saying a compound lottery is some average. It's a lottery over lotteries. It's like a randomization where with some probability you play the top lottery and with another probability you play the bottom lottery. Okay? So the idea of continuity is that if I like this more than this and this more than this, then there has to be some mix of these 2 that I'm indifferent to, that and this $, for sure. So in other words, if lottery A is at least as good as lottery B, and lottery B is at least as good as lottery C, then there has to be some mix of lottery A and C that you're indifferent to, that mix, and $1. So what would that look like? Well, suppose that I said, with probability 1/3, I get to play this game. And with probability 2/3, I get to play this game. This game is currently worth $3 for sure. And this game is worth $0 for sure. So 1/3 of the time I get $3, and 2/3 of the time I get $0. Well, 1/3 times 3 is 1, so that's $1, plus 0 times 2/3, that's 0. So the expected utility of play this 1/3 of the time and play this 2/3 of the time, of that compound lottery, that mixture over these two lotteries, the expected utility of that is $1. This is worth $1. If I'm risk acceptant, I might still prefer that because I like the chance of getting 3. There's still, now, I don't have to be indifferent, but I'm saying if I was using expected utility as my metric, I would be perfectly indifferent between a 1/3, 2/3 mix of these two lotteries and the $1 for sure. So that's the continuity axiom. It says that if you know some preference ranking, A to B and B to C, then you also get to know something about some potential new lottery that's a mix of A and C. Right? So that's continuity. That's our fourth assumption. So now we're reflexive, complete, transitive, continuous. Now those four alone are sufficient conditions. Now we know that there exists a utility function over the lotteries. And you're like, that sounds great. Now we can just assign utilities. I didn't say expected utility was what we were talking about yet. I didn't say that nice simple formula. We want that nice simple formula to be our utility function. And right now we don't have that. We need one more assumption. 4 assumptions deliver us a continuous utility function, but not one with that nice formula. The 5th assumption will deliver the nice formula. Okay? But the 5th assumption is also the controversial one. It's the one that doesn't play out in the lab. It's the one that's easy to break if you're a good experimental psychologist or an experimental economist, an experimental political scientist. Any of these people can come up with contradictions of the axiom I'm about to tell you. Nevertheless, it's a very useful axiom and normatively important. I hope that you will try to live up to the following axiom, even though you might not. Well, what's it called? It's called independence. The independence axiom. And the independence axiom is the 5th assumption, and it's the straw stirring the drink. So this is why it's important that I tell it to you. Even though it's abstract and sounds a little bit wonky, it's also the reason that you get to use statistician expected utility. It's also the thing that people ended up breaking. So this has been the target of a lot of really important dialogue, but it also is important if it were true because it would mean that you could use expected utility as a utility. So what's the independence axiom? Our 5th assumption is independence, and it goes like this. Suppose that you knew that I liked Cupcake Cash. Let's even go with this realized value. So right now this is worth $5. Suppose that you knew that I liked this lottery ticket more than this dollar bill. That makes sense. So suppose that you knew that. Then what that has to mean by independence is the following. Let's say that I mixed Cupcake Cash and this lottery down here, this valueless lottery ticket. Let's say I did an 80-20 mix. 80% of the time I play this game and I get $5. And 20% of the time I play this game and I get $0. So an 80-20 mix of this lottery and this lottery has to be at least as good as an 80-20 mix of the dollar and this lottery. So in other words, the independence axiom tells us the following. The independence axiom tells us the following. If I like lottery A at least as much as I like lottery B, then for any third lottery, C, and any potential mix of the lotteries, I have to like the AC mix at least as much as I like the BC mix. That's the independence axiom. So the idea here is, if you like A at least as much as B, then that means that if you take A and you turn it a little bit into another lottery, then you have to like that result at least as much as the same procedure used on the lottery that you liked less. That's called the independence axiom. That's our fifth assumption. So we're assuming that our preferences over lotteries are reflexive, complete, transitive, continuous, and satisfy this independence axiom. Okay? 5 assumptions. We went from 3 to 5. And here's the punchline. The expected utility function, that nice, pleasant, that simple, straightforward formula, that Excel spreadsheet procedure, 3 columns in Microsoft Excel, that is a reasonable representation of preferences over lotteries, right? So I want to know, when does that represent preferences over lotteries? When does that super easy function do what I want it to in terms of my preferences over the lotteries? Okay? Well, expected utility is a representation of a preference if and only if equivalence, those preferences satisfy those 5 assumptions. So anytime that you behave as a statistician would tell you to, you are acting as if you satisfy completeness, reflexiveness, transitivity, independence, and continuity. We're going to use expected utilities for the rest of this class. There are entire literatures in international relations designed around expected utility. There's what's known as an expected utility theory of war. You'll be calculating several substantively important expected utilities in your problem set. We're going to proceed as if countries maximize expected utilities. That will be what we mean by rationality in our applied sense. But anytime that we do that, anytime that we say here's an expected utility and they maximize it, what we're saying, in essence, is assume that countries have binary preferences over uncertain outcomes, and assume that those binary preferences satisfy reflexiveness, completeness, transitivity, continuity, and independence. So these are our assumptions. I'm spending a lot of time on this because it's really important that you know what the assumptions are. I don't want you to go into this thinking, oh my god, this is all so cool, and then only after do you think about the assumptions. I want you to see that these assumptions play a huge role in our ability to pretend like we know anything about IR, at least through this lens. If you want to see the international world through this lens, then this is the abstract theoretical cost you have to pay. These are the assumptions you have to make. It's an if and only if thing. This is equivalent to studying international relations this way. That if and only if result is a very famous result. It's due to John von Neumann and Oscar Morgenstern in their classic book from 1944, The Theory of Games and Economic Behavior. This was the initial opening salvo of game theory in the world of applied mathematics in the 20th century. One of the most important books written in game theory. Oh, certainly in game theory, but beyond that too. Absolutely hard to overstate the importance of the book. If it weren't for von Neumann and Morgenstern, then nothing in the rest of this class is possible. If it weren't for von Neumann and Morgenstern, if it weren't for the result that I just told you, I wouldn't have anything, we would be done with the class. You think I'm embellishing. Here. This is the standard first year PhD level microeconomic textbook. So, this is page 175. This is Microeconomic Theory by Mascalel, Winston, and Green. This is a standard book for anybody that works in formal international relations to own. You will see this textbook on many bookshelves of people that do strategic international relations. This is part of their training, and this is chapter 6, page 175 out of over 1,000. All right, this is early in the book. The expected utility theorem says that if the decision maker's preferences over lotteries satisfy continuity and independence on top of the usual rationality postulates, then his preferences are representable by a utility function with the expected utility form. It is the most important result in the theory of choice under uncertainty, and the rest of this book bears witness to its usefulness. If you didn't know what we just talked about in the C block, then you would be done with your study. Now, it's boring, and those stupid drawings of continuity and independence are stupid, and you're not going to remember this. I just want you to remember that there were assumptions that got made that allowed us to do what we're doing. And those assumptions are problematic. They can be violated. They can be violated by a human being in a lab. They can be violated by the leader of a country. They can be violated by the members of an opposition group. They can be violated by anybody that has to vote. As we learned on Arrow's theorem, we can violate transitivity pretty easily. These assumptions can all be violated, but if you don't make them, then you're done. This is the trade-off. More assumptions, easier, cooler mathematical toys to play with to study the things that we care about. But the bigger the thing that we want to study, and what's bigger than IR, the bigger the onus to make sure that these assumptions are reasonable, and the more important it is for me as a teacher of this to tell you, a student of this, what the heck is being assumed. Otherwise, I'm just lying to you. Yeah? But if you are willing to make these 5 assumptions, each of which is plausible, but none of which is airtight, if you're willing to make those 5 assumptions, then you can go to Microsoft Excel and calculate an expected utility, and that can be a reasonable method of rationality. Without expected utility, there is no game theory. Without game theory, there is no strategic international relations. Expected utility, as soon as it came out, became the standard way to think about how to evaluate choice under uncertainty. Now, this is important for international relations. Expected utility theorists, in the middle of the 20th century, immediately after World War II, were some of the leading think tank sort of workers at the Rand Corporation and so on, and they used expected utility theory, among some other similar tools, to help come up with a theory of political processes, of international decision-making that was highly and continues to be highly influential in State Department circles. Okay? It's not the only way to see it. It's not the only way that you should learn how to think about choice under uncertainty, but it is a very important one and worth knowing. It is very important for international relations because leaders know that they're rolling dice. They tell us that all the time. All right? International decisions, almost by definition, are uncertain. So we need a simple, easy tool that allows us to know how to evaluate choices under uncertainty. And you're with me on this. You're like, oh, yeah, Theodor von whatever his name, Hollweg, the German chancellor, he said that there was iron dice and he was evaluating the outcomes that could happen and he put probabilities on those, and great. I'm not talking about him though. I mean, I'm talking about him, but I'm talking about you. So the theory of expected utility, the 5 assumptions that we just discussed, they are how I would want my international leaders to make decisions. I would want them to be risk neutral, and I would want them to maximize expected values, which is to say I would want them to live up to reflexiveness, completeness, transitivity, continuity, and independence. I would want them to live up to those 5 assumptions because that's an if and only if with using expected utility. But we know that these are not excellent describers of how everyday decision makers make everyday decisions. Now, starting a war isn't an everyday decision, and the person that decides that isn't an everyday decision maker. Right? So it could well be that international relations is an especially important avenue for expected utility theory because the choices are all important enough and the decision makers have enough information to actually live up to those 5 axioms. But you are going to have risky choices too. You're going to have to decide when to apply to law school, right? Or when to leave law school and start your own startup. You're going to have to decide what kind of stocks to buy. You're going to have to decide when to get a loan. You're going to have to decide all these different things, right? And you're not going to have a chance to know with 100% certainty what's going to happen. You have decisions that in your life are just as important to you as the decision to start a war is to the leader of a country. You're going to have decisions that hard. I mean, that's just life. And there are two reasons for that, at minimum. Here are two important reasons anyway. One of those is that life is just uncertain. There's aleatory uncertainty. The German chancellor cannot know that he's going to win a war, or at present, she's going to win a war. She doesn't know for sure if she's going to win or lose. She doesn't assign a probability of 1 to winning, nor does she assign a probability of 0 to winning any given war. You could think about the hypothetical war between Germany and Austria, Germany and Poland, Germany and Sweden, Germany and Denmark. You could think about all those hypothetical wars that they could start. And in none of them, no matter how strong or weak the opponent would the probability of victory be 1 or 0. You just don't know for sure. Because some of the uncertainty in life is just baked right in. It's what you would call aleatory uncertainty. International processes are so complicated and so big that it's an act of hubris to think that you get to know what will happen for sure. If I go into a mini mart, I have faith that when I buy a Coke and I open the can and I take a sip, it's a Coke. That's a simple, straightforward process. But buying lottery tickets is harder. Going to a casino and figuring out which game you want to play is harder. Starting a war is harder still. You don't get to know those outcomes for sure. Because some uncertainty is just baked right in. I mean, if you know any quantum mechanics, you know that you don't get to know everything for sure down there deep within the atom. We can only think about these things probabilistically. Physicists impose probability structures all the time. Some parts of life are just uncertain. So that's reason one that you need to know how to make good choices under uncertainty, is that uncertainty is part of the human experience, with varying degrees of how important it is for any given phenomenon. But also, there are strategic incentives. So, we'll talk about this a little bit more when we talk about games. But let's just think about a baseball game right now. So in baseball, the simplest part about baseball is there's a pitcher and there's a hitter. And the pitcher and the hitter have directly opposed odds. The pitcher wants to succeed, which would mean that the hitter failed. And the hitter wants to succeed, which would mean that the pitcher failed. It's what we're going to call zero sum in a few weeks. Now, the thing with baseball is the pitcher has a couple of different ways that they can throw the ball, right? They can throw it fast without much movement. That's called a fastball. They can throw a slower pitch that has a lot more movement. That's called a curveball. They can throw a slower pitch that try to throw the hitter off. That's called a changeup. They can throw a really slow one where they don't know what's going to happen. It's random. That's called the knuckleball. There's all sorts of different pitches that they could throw. Different pitchers have different arrays of pitches. Now, if I'm a hitter, I would love to know what kind of pitch the pitcher is going to throw, because then it would be easier for me to prepare. If I knew that you were going to throw a fastball that didn't move, then I would be able to say, okay, as soon as you see the ball swing, because it's moving fast, and it's not going to move very much, so wherever you think the ball is going, just swing there. Don't account for any movement. If I knew you were going to throw a fastball, it would be easier for me to hit it hard. If I knew that you were going to throw a curveball, it would be easier for me to hit it hard. Well, that's why pitchers don't throw the same pitch every time. They have strategic incentives to use probabilistic thinking about their strategy. Pitchers don't throw the same thing every time because otherwise the hitter would know. So consequently, we get to see a wide variety of pitches. We do that because that makes things easier for the pitcher. And we're going to talk a lot about how to choose those probabilities properly. We're going to call that an equilibrium. Wait a few weeks. But even before we talk about that, it's important for you to think about this. There are people in the world, there are people in your life that want to keep you guessing a little. And when they keep you guessing, they're introducing probabilities. Even if it is an aleatory uncertainty that's baked into the human experience and our sensory limitations, even if it's human-made uncertainty, it's uncertainty. You don't know what pitch is coming. You need to make your best choices. And the pitcher, too, has to think, hey, which of these pitches do I most want to... That's hard to think through. You need tools. You need to know when the simplest tool, like in a Microsoft Excel algorithm, is the right tool. Well, we just learned that in the C block. But in the A and the B block, we got a whole framework for how to think about this. And so moving forward, we're not going to talk about you. I mean, not in class. I'm happy to talk with you anytime, although I can't offer you any special insights or anything, but we're not going to be talking about you. But I want you to reflect, and I want you to realize that these 5 assumptions, these rationality assumptions, are normative just as much as they're positive. Which is to say, when I teach them to you, implicitly I'm saying, and this is how you ought to proceed if you have a chance to pause and reflect and think. These are things that will maximize your expected value. These are things that if you take them seriously can help you to make better choices under uncertainty. But we're never going to talk about you. We're only going to talk about countries and firms and organizations and opposition groups. We're never going to talk about you, and I'm sorry about that. But implicit in all of this, implicit in all this study of risk aversion, risk acceptance, expected value, preferences over lotteries, baked into all of this is the fact that I want you to make good choices when you're forced to choose among lotteries too. And even if you don't know the exact probabilities because life doesn't print the probabilities here for you, you can take steps to get good guesses about probabilities. And you can take steps to say, hey, how much do I like any given outcome relative to another outcome? You can be your own expected utility function. And I want you to be. I want you to do that because in expectation that will be what is best for you. And I want to conclude with a final provocative thought. And it's everything to do with the preferences that we've talked about up to this point, both preferences over certain outcomes and now with uncertainty. Your preferences are something that you should think about. You should think about what you value. You should think about how you evaluate risk. You should think about what things are worth to you. You know, that's a process that's going to take some time. You're just getting to that part of your life, and I sound so patronizing right now, but you're only beginning to get to the part of your life where you have to make some difficult trade-off-y sort of choices. And I could be demeaning a lot of hard choices that you've had to make prior to that, and I'm painting in very, very broad brushstrokes, so please, I'm sorry if I offended you. I know that you've had to make hard choices up to this point, but you're going to have more hard ones coming too, I'm sure. And these trade-off choices that you're going to have to make, I can't tell you how to make them. And I don't want to. Your preferences are your business. How you evaluate risk is your business. Okay? But don't let anybody tell you how you feel about these things. If you need, if there's people in your life that you trust and you admire and you respect and whose counsel you seek out, then listen to them. That's fine. But I think people turn to these mathematical models of preferences, both over certainty or uncertainty, and they come out thinking that they're going to know what they're supposed to think. They're going to come out thinking what their preferences are supposed to be, or what their risk attitudes are supposed to be. People go into these things, and it's good for you to think about what a stylized ideal robot fable person would do, what the mathematical robot of the expected utility function will do. It's a useful enterprise for you to learn about that, but only so that you can have a baseline to compare your own preferences against. None of this is my way of saying to you what your preferences should be. Okay? I think it's very tempting to look at all these symbols and this math and all, I went to college for this. People are making choices all the time without knowing any of this. Now this helps, but it is neither necessary nor sufficient for making good choices. What I think is sufficient for making good choices, though, is learning as much as you can, being as deliberate as you can when making your choices. Stop, think, make an Excel spreadsheet, assign probabilities, assign utility numbers. And then, after you've evaluated this as deliberately as you can, do what you think is best. That's all I got. So for the rest of this class, we're going to be evaluating a lot of fake decision makers that live in fake mathematical worlds and have fake uncertainty about fake outcomes. And we're going to assess their choices as analysts and say, this is how they made their choice, and this is what we predict the outcome will be, and so on and so forth. But I just want to make sure that you know that I hope that all of this talk of fake people and fake worlds with fake math and fake uncertainty, in part, has been taught so that you can make better real choices as a real person living with real uncertainty in a real world. Thanks for watching.